All right, good morning, everybody. So, or afternoon, or whenever you're watching this, let's go through and do this practice exam. This is 1411, and this is practice exam 1. Okay, so the first question says read the length of the bar. In order to read anything, you kind of want to figure out how much you know based on these little marks, and then you're always going to guess one more than you know based on the marks. So this, here we go 15 to 16, and there's 9 little dashes between. So these are the ones, and this would be the tenths. So essentially we know this to the tenths. Now if you remember, we said if you have a number like 42.654, this is the tens, this is the ones, this is the tenths, this is the hundredths, and this is the thousandths. So you look at the mark, and then you know based on the marked numbers, you're always going to guess one more. So these all go up by 1. There's 9 dashes between them, which are telling you that these are the tenths. And therefore our answer must go to the hundredths, because 1 after the tenths is the hundredths, meaning D would be our answer. Okay, number 2, answer the following calculation. So, all right, so let's go ahead and do this. We have 249.362 plus 41, so let's start with that. 249.362 plus 41, and that gives us an answer of 290.362. But when we add, we look at decimals. Remember, when you add or subtract, you look at decimal places. When you multiply or divide, you look at sig figs. This had 3 decimal places. This had 0 decimal places. Therefore, this answer should have 0. So we underline up through the decimal place. We're not going to get this, but we're up through the decimal, meaning we know this ones place. We know all 3 of these numbers. Now we can divide it by the 63.498. And I get an answer of 4.572739, yada yada. But we divided, and when you divide, you look at sig figs. Now this number right here, we underlined the decimals to tell us how many sig figs there were for the next one. So this has 3 sig figs that we underlined. This one has 5. What's smaller, 3 or 5? The answer is 3. We underline that. Ask if this is 5 or greater. It is not, and 4.57 is our answer. Okay. Here we're converting 5 micrometers to nanometers. So that's 5 times 10 to the negative 6 meters. We did it 2 ways, so I'll show you both ways. So the first way is just to replace the micro with times 10 to the negative 6. You go like this. If this is meter, we put meter here. We're turning it into a nanometer up here, and we know there are 10 to the negative 9 meters in a nanometer. We know when we divide exponents, we subtract. So this is 5 times 10 to the negative 6 minus a negative 9. When you subtract a negative, it's the same thing as adding a positive. So negative 6 plus 9 would be positive 3 nanometers. That's one way to do it. The other way I showed you how to do it is anytime you just take like micrometers and nanometers, and we're converting it this way. This is negative 6. Ignore that. And this is negative 9, and we just subtract them. Negative 6 minus a negative 9 gives us also a positive 3. So we'd say 5 times 10 to the 3rd nanometers. Both ways, obviously, will give you the same answer because they're exact same process. Just a different way of thinking about it. Okay, so this next one says the recommended dose of alixophilin, a drug used to treat asthma, is 6 milligrams of medicine per kilogram of body mass. Let's calculate the dose in milligrams for a 112-pound person. Okay, so one thing that we're going to make sure that we do here is pay attention to, because we have 2 units of mass here, we have to pay attention to the fact that this top one, the milligrams, is of medicine, and this kilograms is of body mass. So if I rewrite all the numbers that we have real quick, here's what we got. We have currently 6.00 milligrams of meds per kilogram of body mass. We have a pound is 453.59 grams per pound. And you could have put pound and 453.59 on the bottom. This is just more the way that we're used to seeing it. And we have a 112-pound person. In other words, 112 pounds of body mass. I don't know why I can't spell body mass. All right, so we're gonna try to put these together in a way that makes sense. The thing with one unit is this one, so that's one we want to start with. 112 pounds of body mass. I'm just going to, well, I'll just write the whole thing, body mass. Okay, in order to use this one, we have to get it into kilograms, and that's why this thing's here. That will help us get into grams, then we know how to go to kilograms from there. So if this is pound of body mass, essentially this can be pound, in a pound of body mass, there are 453.59 grams of body mass. Or we can just keep it as pounds. In a pound, there's 453.59 grams. That got us to gram town, and eventually we need to get to this kilograms of body mass over here. All right, but to get to kilograms, we're in grams. We know we want to go from grams to kilograms. So you can just straight up write it out, but then you have to ask yourself how these two things relate. Well, hopefully you remember kilo is 10 to the third. So there are 10 to the third grams in a kilogram of body mass. And this again is body mass. All of this over here was talking about body mass. All right, now if this is kilogram of body mass, we can take this and put it down here. We know in 1 kilogram of body mass, you can take 6.00 milligrams of the meds. Okay. And now we're all set. So let's go ahead and calculate this out. So clear it. We got 112 times 453.59 times 6.00, which we don't need, divided by 1,000 or 10 to the third, however you want to put it, and hit enter. We get an answer of 304.8 milligrams. But this has 3 sig figs. We said, well, look at this as infinite, infinite. This is likely a measurement because they based it based on research, etc. So that has 3. So our final answer should have 3. We underline those 3, ask if that number next to it's a 5 or greater. It is, and 305 milligrams would be our final answer. All right. Moving on to this next one, milk. Okay, so anything that you can filter stuff out of is considered heterogeneous. Homogeneous, remember, is the same. Heterogeneous is different. But the way that we think about it is if it's the same, it has high clarity. That doesn't mean it's clear. Kool-Aid has a high clarity. So like well-filtered sweet tea has a high clarity. Those are all homogeneous mixtures. Something that's different would be anything that is cloudy. Mud, sand water, etc. Milk, if you think about it, if you shine a light through milk, the light does not penetrate through to the other side. It gets stuck up in there. That's because milk is technically heterogeneous. It's homogenized, meaning they mixed it really well, so it stays well mixed, but you can filter pretty easily the fat and the proteins out of milk using a small enough filter. So that is why it is heterogeneous. Anything that's homogeneous, you can't filter stuff out of it. But anything that's heterogeneous, you can filter things out of it. All right, this next question, determine the number of protons, neutrons, and electrons in the following. Okay, so this thing has 12 protons. It's got 12 protons. We're actually talking about magnesium here. I didn't need to write an X. I could have also written magnesium, and you would have had to know that that was 12. So that essentially takes us down to those 4 choices. Then if you remember, the number of neutrons is got to be 25 minus 12, which would be 13. So the number of neutrons this thing has to have is 13, which essentially takes us to this one in that one. Last but not least, we need to figure out the number of electrons. If it's got 12 protons, it has no charge written here, which tells us it's neutral. That means it must have 12 electrons. So our final answer is that one, C. All right, moving on to this next one, excuse me. So we have X107 and X109, and it wants to know what X is. All right, let's walk through this sucker. The very first thing you do, if you remember, is you find the two that add up to 100, and those are the percentages you're going to focus on to move the decimal. So I move that decimal twice, 1, 2 times. So now that decimal there no longer exists. And now they're decimal percents, they're not percents. So this is 0.5184 and this is 0.4846. Now you multiply them together, each one. This is a weighted average. And I can kind of figure out already, like, check it out. If you have some kind of sample of some X isotope and half of it, roughly half, 51.84, has a mass of 107 and the other half has a mass of 109, if I asked you the mass of that thing, you'd be like, it's about 108. This is almost like a regular average. But we're going to do the weighted nevertheless. So it's going to give us an answer about 108, and we should already be guessing that. But there's a little more 107, so let's see how it turns out, okay? Okay, so first things first, multiply those together. 106.90509 times 0.5184. And I get 55.41959. Let's go crazy here. Okay. Then I do 108.90476 times 0.4846. That gives me an answer of 52.7752467. All right, whenever you multiply, you look at sig figs. This one here had 4, and this one here had 4, and these had a lot more than that. So these each have 4 sig figs. We're keeping all those numbers though, and I'm going to add them all up. And I get an answer of 108.1948. So you can already guess which one the answer is. Let's keep looking though, because when we add them up, just in case I didn't give you this, in case this is a short answer, I'd want to know how many decimal places there are at the end. If this one, when you add, you look at decimal places, this one has 2 decimal places. This one has 2 decimal places, so this one should technically have 2 decimal places, and that's why your answer is 108.19. All right. Okay, this says silver has an atomic mass of 107.868 AMU. Now, it gives you an isotope mass of 1 and it asks you for the isotope mass of the other. These here, in the previous examples, are both isotopes. But here, it gave you this total and asked you to find one of those, okay? So just to kind of remind you what we've been doing, you take the isotope mass and you multiply it by a decimal percent, plus the isotope mass of the other times its decimal percent, on and on and on, and they all equal the atomic mass. So wording is important here. So I'm going to rewrite it real quick. Hopefully you agree. We take the isotope mass of some A, and we multiply it by the decimal percent of A. And then we add the isotope mass of B times the decimal point of B, or decimal percent of B. And this all equals the atomic mass, right? So we multiply them together and then we add them up, and that gives us the atomic mass. So in this situation, we don't have the luxury of being given this stuff to find this. Instead, we're given the atomic mass, which it tells us is 107.868. And it says the isotope of one of them is 108.905 times 0.48161 would be its decimal percent, plus some new isotope mass, which we don't know, we'll call X. And can we figure out the decimal percent? If one of them makes up 48%, the other one must make up the additional like 52-ish percent. Let's find out exactly what it is, just so I don't mess up when I'm on camera. But 100 minus 48.161 gives us 51.839%. So this other one is 0.51839. So these two should always add up to equal 1. Okay, so now we're kind of sitting golden. We can multiply those together, and we're solving for X. So let's go through the math just to make sure you're comfortable with it. In fact, I'm going to grab another piece of paper here. Okay, so starting with this one, we'll do 108.905 times 0.48161. And this right here gives me 52.4497. When you multiplied it, it gave you something with 5 sig figs. So I'm going to keep 1 extra sig fig. I always keep 2 extra sig figs. We haven't practiced it a lot, but that's what I usually like to do. As long as you keep 2 after how many you need, you're good. And then plus X times 0.51839 is equaling 107.868. Okay. We have this, and we're going to subtract that 52, because again, we're trying to get X alone. This is just algebra. That had 3 sig figs in it. Okay, so that goes away. Now I'm just going to subtract 107.868 and then just change the negative sign. So this right here would give us 55.418. So we have X. .26. Okay, now we subtracted here, so you look at decimal places. This had 3, this had 3, so this should technically have 3 decimal places. Now we're sitting pretty, because now all we have to do is divide by 0.51839. And that will give us our X. And X equals 106.9, and then let's make sure 90458. Let's look at sig figs now and decimals. So we divided. So this one had 5 sig figs that we had underlined from the previous part where we subtracted, and this one also has 5. So this therefore should have 5, and our answer is 106.90. And it would be atomic mass units or grams per mole. I'm comfortable with either. Okay. Moving on. All right, so it asks us how many oxygen atoms are 2.50 grams of silicon dioxide. So remember, we go from grams to mole to molecule to atom and back. Now, one common issue when we're asked about atoms is that people use the mass of the atoms, but it's talking about silicon dioxide. So we need to find the molar mass of silicon dioxide. So to do that, we need the mass of silicon, which is right here, 28.09. And I'm going to add to that 2 oxygens. So I did 28.09 because it was silicon dioxide, plus 2 times 16.00 for the oxygens. And that gives me a mass of 60.09 grams per mole. So here, our conversion is going to be 60.09 grams per mole. Okay, over here on the next one, we want to go from mole to molecule. So you ask yourself how many molecules are in a mole. Hopefully you agree that there's 6.022 times 10 to the 23rd anything in a mole. And last but not least, molecules to atoms. It talks specifically about oxygen atoms. So therefore we need to look at oxygen atoms. In one silicon dioxide, which is an Si with 2 O's, there are 2 oxygen atoms in a molecule. Now I use a little X after the O. It's not technically, it's not there. Oxygen is just an O, but I use that X to make it not look like 20 because I get so many questions on that. So that is why I do that. Okay, I think we're good to go. Let's start with what we got. We have 2.50 grams, right, of SiO2. If this is grams of SiO2, we have to put grams of SiO2 here. There are 60.09 grams of SiO2 in a mole of SiO2. Now we're in mole town. We need to go to molecule town. If this is mole, we're going to put mole down here. And then what's left is 6.022 times 10 to the 23rd. Molecule. If this is molecule, I have to put molecule down here. We know in a molecule, there are 2 oxygen atoms. So let's go ahead and do this calculation, shall we? We got 2.5 times 6.022 times 10 to the 23rd times 2, and then divide it by 60.09. That gives me an answer of 5.01 times 10 to the 22. This had 3 sig figs, this was infinite, this has 4, and this has 4. All right, and again, that's oxygen atoms. So that would be your answer. Moving on. Okay, so hopefully you remember very boring, okay, where violet has a wavelength of about 400 nanometers, about 450. Blue, we were looking at about 500. Orange, we're looking at about 600, and red was about 750. Okay, these are nanometers. Hopefully you also remember that if you have an increase in wavelength, your frequency must decrease because we said C equals lambda nu and C is a constant. So if one increases, the other one must decrease. All right, given that information, it says which type of electromagnetic radiation has the lowest frequency. If we're looking for the lowest frequency, this also means the highest wavelength, okay? So going this way, hopefully you see orange has the highest wavelength. Red isn't on here, but red would have had the highest wavelength. And if you want to fill in the other colors, it goes red, orange, yellow, green, blue, whatever, purple, violet. So it would be just like a regular rainbow, okay? And yellow would fit somewhere between 6 and 500, and green would fit somewhere between 6 and 500, and it's kind of all mishmashed together. So, so for this question, the one that's the highest that I can see is orange because it's 600 nanometers, and there is no red. But if there had been red, that would have been my answer, but because that didn't exist, orange is our answer. Okay. Moving on to more questions regarding light. It says calculate the frequency of the light emitted by a hydrogen atom with a wavelength of 384.2 nanometers. Okay, so There are a few things we could do, but let's go back to our original equation, our big equation. It's E equals h nu equals hc over lambda equals negative 2.18 times 10 to the negative 18 times 1 over n final squared minus 1 over n initial squared. We'll use it a lot. We'll use it for all these problems to do with light. And if you have this one memorized, you're set. Okay, it asks about frequency. It says calculate the frequency. The only thing with frequency is this portion, and then it gives us wavelength, which is this portion. Those two we're going to set together. So frequency equals h nu equals hc over lambda, but you have h on both sides, so they just cancel out. So we have nu equals c over lambda. We know that in order to do this, this must be in meters. Okay? You don't have to convert it to scientific notation or anything. You can just replace the n with times 10 to the negative 9 as so. So it says to calculate the frequency, so we're trying to solve for that. We know c is 3.00 times 10 to the 8 meters per second. And we'll put it all over the wavelength given, which is 384.2 times 10 to the negative 9 meters. You have to replace that little n. Let's go ahead and figure it out. Remember, anytime you have more than two things being multiplied in the denominator, it helps just to throw a division sign in front of each one, unless you use parentheses around here. Otherwise, your calculator doesn't understand PEMDAS. So 3 times 10 to the 8 divided by 384.2 divided by 10 to the negative 9. And that will give me my answer of 7.81, because this only has 3 sig figs, times 10 to the 14 hertz, or inverse seconds, or seconds to the negative 1. Doesn't matter. All right, moving on. It says how many photons are contained in a flash of green light that contains that much energy. That's a big amount of energy if you remember. Like if you have kilojoules, that's a huge amount of energy. So how many photons are contained in a flash of green light? We're looking at, we need energy and we're given wavelength. So in our equation, E equals h nu equals hc over lambda. I'm going to stop right there because I see wavelength and I see energy. So those two I'm going to put together, where I have E equals hc over lambda. Those are the two parts of the equation I'm going to use. And remember that this E is an E of a single photon, or it's sometimes the energy of a photon that's been absorbed, or the energy of the atom after a photon's been absorbed. So, so keep in mind, this is just for one little thing. So it should be a tiny amount. Let's go ahead and figure it out. Our H equals 6.626 times 10 to the negative 34 joules times seconds. Our speed of light is 3.00 times 10 to the 8 meters per second. And we're putting all of this over our lambda, which is 525, but don't forget, times 10 to the negative 9 meters. You have to replace this with times 10 to the negative 9. All right, let's go ahead and calculate it out. 6.626 times 10 to the negative 34 times 3 times 10 to the 8 divided by 525 divided by 10 to the negative 9. And I get an answer that makes a lot of sense. It's 3.78629 times 10 to the negative 19. Our meters cancel, our seconds cancel, and we're left with just joules. So I'm going to rewrite it over here, joules. So we got 3.7869, or 8629 times 10 to the negative 19, and that would have just 3 sig figs. Okay, so that's a tiny amount, right? This is a small number. So if you remember, we said, essentially, if you got a flash, you have like a whole bunch of these little small numbers. So this is one tiny little photon, but in order to get this many, you had to have a whole bunch of photons. So this is like the potato issue, where if you have a sack of potatoes and one potato, and I tell you one potato weighs 0.5 pounds, but this sack of potatoes weighs 20 pounds, and I say, how many potatoes are in this sack? Well, you'd say, Well, 20 pounds divided by 0.05, or divided by 0.5 pounds equals 40 potatoes. And you'd be right on the head. There are 40 potatoes in this bag, most likely. Now this is a bundle that all together adds up to 189 times 10 to the third joules, a whole bunch of energy. But one single one of these photons is just this tiny amount of energy. So when I ask you how many there are, well, you take the big number divided by the small number. And we're going to divide it by 3.78629 times 10 to the negative 19. All right. So 189 times 10 to the third divided by 3.78629 divided by 10 to the negative 19. And I get an answer of 4.99 times 10 to the 23rd, which happens to be answer D. All right, last but not least, what is the energy of light associated with a transition? So it says it's going from an n equals 3 to n equals 8, meaning that electron is popping up. If that electron's popping up, we know that it's absorbing. Okay, remember, if something goes from lower to higher, I'm not even gonna be able to draw them all, but it went from a 3 all the way up to an 8. So in order for it to go up, it had to have gained energy. So you know it's absorbing. So that eliminates all but 3 answers. Okay. Nevertheless, let's go and figure this out. So we have to look at our original equation. E equals h nu equals hc over lambda equals this whole number times 1 over blah, 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 blah. So it gives us the energy, or asks us for the energy, and it gives us the ends. So these are the two portions of the equation we're using. So when we set them equal to each other, which we'll do, we're saying E of the photon that was absorbed is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n final squared minus 1 over n initial squared. All right, so we need to find the energy, but we know these transitions. We know it started at 1, and we know it ended at 8. It went from a 3 to an 8. In other words, our final is going to be the 8, and our initial is going to be the 3. So let's go ahead and plug those numbers in. So we'll have 1 over 8 squared, which would be 64, minus 1 over 3 squared, which would be 9. All right, in order to calculate this, let's first calculate each of these individually. So the way I would do that is in parentheses, I'd say 1 divided by, you do 8 squared, end parentheses, minus, another parentheses, 1 divided by 3 squared. Whoops. And you hit enter. This gives me a negative number because again it's being absorbed, 58611 essentially. And now I take that number and I'm just going to multiply it times the negative 2.18 times 10 to the negative 18. And I get an answer of 2.08 times 10 to the negative 19 joules, which is how much energy it would require for an electron to go from the n equals 3 level, this IR area, to be pushed up to an 8. And that is why A is our answer. Again, it was absorbed because it went up. All right, I hope that helped. Good luck on the exam, you guys.